Main purpose of today's discussion is to understand how the inlet actual flow rate versus the speed surge control is implemented. So let's start the discussion. This is again a compressor which has inlet pressure, temperature and flow measuring device installed, and it has anti-surge control valve which is recycling back to suction, and then discharge side one check valve is installed and discharge valve is also installed, and then it is connected to system header pressure. So surge control, inlet actual flow rate versus speed, which is also known as Q by M. So FT is a flow measuring device at inlet of compressor. It can be mmWc. PT is inlet pressure of the compressor in bar gauge. TT is inlet temperature of compression degrees Celsius. And a speed is a speed of compressor in RPM. PT, TT and PDT of FT are connected through electrical signal to PLC or DCS. In addition to these, all other instrumentations and control valves are connected to PLC or DCS. Surge control, actual inlet flow rate versus speed. Converting PT, TT and PDT data in engineering value in PLC. So, and after this, actual inlet flow is calculated based on the differential flow dP, that is dP flow or flow dP, pressure at flow measuring this device, that is PT, temperature as flow measuring device, as TT. So using FT, PT and TT, actual flow measurement can be done or calculation can be done in PLC. Design inlet actual flow rate and design speed are fixed value, that is already provided, and so putting all this data in an equation we can calculate the surge control logic. Surge line, surge test of compressor is conducted from minimum 3 IG position or 3 speed position or 3 different speed or maximum any other number of points. As this is used for variable speed compression, and so surge test data at field is difficult and factory test data are always provided. The speed ratio N by ND is drawn on x-axis and inlet actual flow Q by QD is on y-axis, where N is operating speed in RPM, ND is a design speed in RPM, Q is the operating inlet actual flow rate meter cube per hour, and Q is the design inlet actual flow meter cube per hour. So N by ND is drawn on x-axis, Q by QD or is drawn on y-axis. Inlet actual flow rate upon design inlet actual flow rate is y-axis. Slope is calculated on average of surge test data. So it's, for example, it is coming surge slope is 0.68 is coming and bias is always 0. So we can have slope of 0.68 based on Q by QD on y-axis, N by ND on x-axis. Surge control line, surge slope is 0.68, bias is 0. Let's say surge safety margin on the surge slope is 10%. So surge safety margin 0.68 into 10 upon 100, 0.07. So surge control slope will be surge slope plus surge safety margin. So surge control, not bias, it is wrongly written bias, it should be slope. So surge control slope is equal to 0.68 plus 0.07 is 0.75 constant. And surge control bias is equal to surge bias with 0. So surge control slope is more than surge line slope, and that is why it is on top. Based on again N by ND on x-axis, Q by QD on y-axis. Operating point, design speed ND is 14,000, let's say RPM. Design inlet actual flow QD is 8,000 meter cube per hour. Operating speed N is 12,000 RPM. Operating inlet actual flow is 9,000 meter cube per hour. So operating speed ratio N by ND is 12,000 upon 14,000 is coming 0.86. Operating inlet actual flow ratio is equal to Q by QD 9,000 upon 8,000 is 1.13. So if you see, this is the operating point on N by ND upon Q by QD, and which is safe zone. PID controller, proportional integral derivative controller, developed in PLC or DCS. Input data are process value, PV and set point, SP. One controller output. Output of PID control will give command to anti-surge control valve through 4 to 20 milliamperes electrical signal to position of anti-surge control valve to operate it. Process value, inlet actual flow ratio Q by QD into F upon operating speed ratio, that is N by ND. This is again operating inlet actual flow ratio Q by QD into F upon operating speed ratio N by ND. Set point is average of surge test data of Q by QD upon N by ND plus surge safety margin into bracket close into factor F. Factor F can be 1 to positive with any value number, any number. Typically it is 100. So PID logic, if PV is greater than SP, then anti-surge control valve will close. If PV is less than SP, then anti-surge control will open. And if PV is equal to SP, then anti-surge control valve will be in the last position. Anti-surge control valve operation, let's assume operating inlet actual flow ratio Q by QD is 1.13, which is constant. Operating speed ratio N by ND is 0.86, which is constant. So this is the point of operation. Surge slope is 0.68. Let's say 10% margin, 0.68 into 10 by 100, 0.07, constant. Surge slope with margin is surge slope plus safety margin. So surge slope with margin 0.68 plus 0.07 is 0.75, constant. Set point is surge slope with margin into factor F. So set point will be 0.7 into 100 is 75, constant. Operating slope is equal to operating inlet actual flow ratio Q by QD upon operating speed ratio N by ND. So operating slope is equal to 1.13 upon 0.86, which is coming as 1.13 constant. Process value, operating slope into factor F. So 1.13 into 100 is 131, constant. So logic of PID, PV, which is 131, is greater than SP is 75. So PV is greater than SP, anti-surge control valve will close. So if compressor operates above surge control line, it is safe and anti-surge control valve will close. However, if operation is below the surge control line, it is not safe and anti-surge control valve will open. So thank you. With this, I have finished this discussion. Hope you will like this. If it is so, please subscribe my channel, like it, share it, so that you will get the intimation of new videos. See you in the next discussion. Till then, bye bye. Thank you.